Great. Well, thank you all so much for coming. We're really excited to kick off the GeoDAWG seminar series this fall with a really great talk from Harriet Turner. Let me go, next slide. Okay, just from our quick normal updates. This seminar is recorded and will be uploaded to our YouTube channel once it's concluded. And you can access that link through our website, and Harriet's name here that you can see on the bottom left-hand side will become a hyperlink that will take you directly to that video. So please come back and check that in the future. We'll also have all of our previous recordings and seminars also there if you'd like to peruse them at your own time. The website has a lot of great resources. If you haven't joined the mailing list, we advise you to please do so. We send out just some updates to the mailing list about upcoming workshops that are relevant and any upcoming discussions that we have and so forth. So please come and check that out. Before jumping into this seminar, though, we do have a really quick announcement. We had a really great GeoDAWG workshop this summer in Germany. That went really, really well. And we'd also like to welcome our new co-chair to the GeoDAWG workshop, David Thummins, who's doing a really great job. And we are going to be having a follow-on workshop to that follow-on discussion to that workshop in 2 weeks' time in October. That will be at during our normal GeoDAWG time, which is 11 a.m. Eastern time. And you can use the same Zoom link that you use here for the seminars, and we'll kind of give quick updates in the first 15 minutes and then save the remaining time for discussion about the workshop that we have there. And just a quick rules of the road. Harriet is okay if you interrupt her with talks, but please raise your hand and we'll call on you. And then you can ask your questions. Also, please feel free to enter them in the chat or save them for the end. We'll have plenty of time for a discussion. Then if you could remain muted during the talk, just so that we limit any distractions for Harriet, that would be great. And I'm really excited to be introducing Harriet, our very first seminar speaker for this summer. Harriet is a PhD student at the University of Reading. She's done a lot of really great work on solar wind data assimilation and space weather forecasting. And today she's going to be talking about, I believe, a recently published paper of hers on solar wind data assimilation in an operational context. So I will mute myself, stop sharing my screen, and let Harriet take it away.
Great, thank you. I'll just share my screen. New laptop, it's not going to let me do it. There we go. Let's try again. Can you see that?
Yes, we can. If
yeah,
you go
I'll just
to
put it in full screen.
Perfect. Yeah, works.
Great. Okay, yeah, so my name's Harriet. I'm a, fourth year PhD student now at the University of Reading, supervised by Matt Owens and Matt Lang, and also with some help from the Met Office down in Exeter as well. And my talk today is, as already said, solar wind data assimilation in an operational context, the use of near real-time data and the forecast value of an L5 monitor. So I'm not sure entirely what the background of everyone here is, but a little bit of introductory information about the solar wind. So it's a constant stream of charged particles that flows off of the sun and fills the heliosphere or the solar system. It's comprised mostly of electrons and protons. And this is a bit of an artist's rendition of it. It should be noted this is not to scale. And it is structured in a way, in a spiral configuration due to the sun's rotation. So the solar wind drags out the sun's magnetic field. And because the root of these magnetic field lines are rotating, it pulls the structure into into a spiral shape. So the solar wind flow is mostly radial, but due to the rotating magnetic field, we get streams of fast and slow solar wind. So although the particles are actually moving out radially, because the magnetic field is being rotated, these structures go round. And with respect to Earth, the sun rotates with a period of 27 days. So you can see this rather slow animation. It would take a stream 27 days to make a full solar rotation. And looking at that as a time series from Earth's orbital radius, it would look something like this. So this is a modeled solution, so it's a lot smoother than anything we would see observationally. But you can see that where we have these faster streams, you get these sharp increases in solar wind speed, and then a slow decrease back down to the slower speeds. So the solar wind is sort of the background conditions, and we get these big eruptions on the sun called coronal mass ejections, or CMEs, and they're huge eruptions of solar material, and they're the main driver of severe space weather on Earth. So they propagate through the solar wind. So these background conditions can affect their speed and arrival time. So this animation here is just an example, a modeled example of how a CME front can be altered by the solar wind conditions. So you can see that this one's injected sort of close to a boundary between fast and slow solar wind. And you can see that this fast stream is acting to accelerate that part of the CME, whereas the slow stream, it will be acting to slow it down. So if we know the background solar wind conditions better, then it should help us to forecast CME speed and arrival time better, in theory. So this is just an example of how big CMEs are. So this white line is the outline of the sun. So you can see just how big these eruptions are. So why should we care about any of this? Space weather, or the changing plasma conditions in near-Earth space, poses a significant threat to modern technology. I realise some of you are probably in the US, but extreme space weather is on the UK's National Risk Register. So this is actually an updated version for this year. I know it's a very thrilling schematic, but just a few examples is pandemics, which has actually increased in likelihood since the previous version of the risk register. There's coastal and river flooding, heat waves, and severe space weather, which has also increased in both likelihood and impact since the last one was released. So they're sort of starting to take severe space weather a little bit more important, a little bit more seriously. But it can have a wide impact on Earth. So it can induce currents in the ionosphere and thus induce currents in the wires, and that can cause a lot of damage to transformers and power stations and lead to blackouts. Can be damaging for astronauts and for crew and passengers on high altitude flights. Damage satellites and GPS, but it can create brighter aurora, so it's not all bad. But current solar wind forecasting is typically done using a model for the corona, or the sun's outer atmosphere, and this is coupled to a heliospheric or a solar system model. So we have the sun and the Earth with an average distance of 1 AU between them. And the coronal model takes photospheric observations, feeds them into a model, for example, WSA or Wang-Shili-RG, but other coronal models are available. And this gives us boundary conditions at 0.1 AU. And we get from that a solar wind velocity and also a magnetic field. This can then be used in the heliospheric model. For example, Enlil, again, there are other options available. And out of Enlil, we get solar wind speed, magnetic field, number density, and temperature. And these can then be propagated up to Earth to produce a solar wind forecast. Solar wind forecasting has, starting from the original photospheric observations, they're essentially free running, so they do not take in information from observations to constrain them. So this is where the DA part is coming in. So I'm sure, as a lot of you know, DA combines prior information, usually from a model, with observations to find an optimum estimation of reality. And it's been used a lot in numerical weather prediction, and which has led to large forecast improvements. However, it has been underused in space weather. It's very much in its infancy in space weather forecasting, but has been used in three main areas: the photosphere, solar wind, and ionosphere. So the photosphere, which is the lowest layer of the sun's atmosphere that's observable, and the ionosphere, where it's most advanced, is where the Earth's atmosphere reaches space. So using DA in the solar wind, I've been using the Berger radius variational data assimilation scheme developed at Reading, which it was actually written by one of my supervisors, Matt Lang, and it combines observations with a steady state solar wind model. And we use the prior inner boundary condition from a coronal model. So I'm just going to go through a little bit how it works. I want to caveat this by saying I have not been involved in developing the methods for Bravda. I've been more on the verification side. So any really technical questions, I may struggle. So yeah, I'll just bear that in mind. But so if we have an observation at 1 AU taken at time T0, we will then use, we use a solar wind model called HUX, and that is, we use the adjoint to then map this backwards in time, because if we were to update the model in this at 1 AU, any improvement we would see would just get swept away out to space, just because solar wind flow is radial and no information goes back towards the sun. So we essentially need to run this backwards and take that observation back towards the inner boundary of the model, which in this case, although this schematic is a little bit misleading, it's at 21.5 solar radii, or which is 0.1 AU, rather than the sun's surface. And once we have mapped it back to the inner boundary, we update those inner boundary conditions. And then that allows us to propagate that improved inner boundary condition back out, which can then be run forwards in time using any model, but in this case we've used the same model again, so using HUX, the steady state solar wind, and that can be propagated round to Earth to give hopefully an improved forecast, as we should then, because of those observations, know the background solar wind conditions a bit better. So as I said before, the current forecasting is typically a coronal model coupled to a heliospheric model. So the DA implementation takes the inner boundary condition, it goes into Bravda, goes forwards in time, takes those observations, then goes backwards, updates the inner boundary, then goes forwards again to produce a solar wind reconstruction, which can then be used at Earth. There are a couple of different methods that you can use. So previous work looking at Bravda has used the reduced physics model Hux-T, which is a little bit different from Hux, which is the one we've used in Bravda. The naming conventions are a little bit confusing sometimes, but Hux-T is the time varying model. But for simplicity in my work, I have just used co-rotation. So this essentially assumes that the sun remains constant as it rotates. So an observation taken at 1 AU can then be used as a forecast for Earth sometime later. And that time depends on the longitudinal separation between the points. So the Hux method takes the updated solar wind speed from Bravda and the magnetic field from the inner boundary, goes into Hux to then be used as a forecast for Earth. Whereas for co-rotation, we just take that updated solar wind speed and move it forwards in time and basically say that the next solar rotation will look the same as the one we have just reconstructed. So the observations I'm using come from the STEREO spacecraft. So that stands for Solar Terrestrial Relations Observatory. And it was a twin mission with Stereo A and Stereo B, standing for ahead and behind. So they're in Earth-like orbits, but separating in longitude. And they were launched in 2007. Communication was lost with Stereo B in 2014 because the two spacecraft passed behind the sun. And they were to be powered down during that time. But during a test of that, they powered down Stereo B, but then couldn't regain communication with it. So unfortunately, we lost that source, but Stereo A is still operational at time of speaking. Yeah, so that's just a little schematic of how it works. So they got launched and Stereo A was on a slightly faster orbit. So it was ahead of Earth and getting further ahead in longitude, whereas Stereo B was falling behind. I'm also using observations from the L1 point, which is on the Sun-Earth line, but about 99% of the way from the Sun to the Earth. So this isn't to scale. And we have ACE, which is the Advanced Composition Explorer, launched in 1997, and the Deep Space Climate Observatory, or DISCOVER, which was launched in 2015. And both of these are giving near-Earth observations from L1. So again, not scale. So this is just an example of the output we might get from Bravda. So this is the polar plot, so looking down on the North Pole of the Sun. You can see that with the prior, so before the DA, and the posterior after DA, that there has been quite a lot of change between the two. So for example, this fast stream here has increased in width. This one has massively decreased in speed. This one's pretty much disappeared. So you can really see that that the DA is really updating our knowledge of the system given those observations. And similarly, as a time series at 1 AU, so at Earth's orbital radius, we can verify it at 3 positions, so at Earth, at Stereo A and Stereo B. And you can see that the posterior, looking at the mean absolute error, is doing better. So it is improving our knowledge of the background conditions. So just a little bit more about how I'm producing the forecast using the output. So we have just an example of a solar wind time series. So that's our assimilation window. So we take in 27 days worth of observation, so a full solar rotation's worth. And from that, we reconstruct a solar wind and then shift it forwards in time and use that 27-day reconstruction as a forecast for the next 27 days, giving us our forecast window. But for Bravda to be operational, it needs to be able to work with real-time data. So all previous experiments have used science level data, which has been pre-processed to provide a cleaner data set. So my previous work and also some work by my supervisors has also used this science level data. And this removes data gaps, anomalies and biases. So in general, it just looks a bit nicer and is just much cleaner than the raw output you might get. And looking at the comparison between the science data and the real-time data, you can see that there are some issues with that real-time data stream. So in the ACE data, you can see that there are these sort of step changes in solar wind speed. The stereo A data they follow pretty closely, so that's pretty good. But the stereo B data is, it's gone a bit wild. There's biases, there's a lot of noise in there. Through a bit of digging, I did find out why, and it turned out just to be an issue with the real-time data, the sensor. And there were NASA politics involved that I don't really want to get into, but it was causing issues in that stereo B stream there. And similarly with Discover, you can get these big spikes in solar wind speed. This tends to happen when the solar wind density decreases, because the way the sensor works on the Discover spacecraft is it infers the solar wind speed using density somehow. I'm not entirely sure exactly how, but when the density drops low, then sometimes you get these big spikes in speed because it just can't work out. It can't infer what the solar wind speed is from that density. So we wanted to see how this might affect the data assimilation. So we're assimilating all sources of observation, so from stereo A, B, and ACE, and evaluating the forecast accuracy at those 3 observation locations. So we're verifying this against the science data, as we see that as being the best representation of what we think the truth is. So we compare forecasts made using prior, the real time, and the science data. So I realize there's a lot of lines on this plot, but on the y-axis, we've got the mean absolute error. And on the x-axis, we've got forecast lead time in days. And we look at 2 time periods. So we've got 2009 to 2011 and 2012 to 2013. So these sort of represent a time close to solar minimum and a time close to solar maximum in this later one. And we also compare it to just purely L1 co-rotation, which is using no data assimilation at all. So just taking the observations from L1 and kind of using it as a persistence forecast. So we can see that in both cases, the data assimilation forecasts for both real-time and science data are performing better than the prior, which is good. So we're improving the forecast by assimilating the observations. We can also see that most of the time, the real-time is not that much different from the science data, particularly in this earlier want. I should also add that we are mostly, well, in both cases, we are performing better than L1 co-rotation. But you can see there's a bit of divergence for lead times greater than about 6 days in this solar maximum period, which doesn't, well, it didn't really make sense when we first started looking at this, because you would have thought that the science data would be better at forecasting the science data than the real-time data. So we did a little bit of digging into why this might have been, and that led to using a Taylor diagram, and these are used quite a lot in meteorology to compare different forecasts. So we've got 3 different axes. We've got the mean absolute error in this purple, sort of arcing this way, correlation coefficient in these slices, radial slices this way, and the standard deviation going this way. And the idea is that you want your forecast to get as close to the observations as possible. So you can see these are sort of clustered into 3 areas. We've got the prior forecasts here. Oh, we want to get close to the observation. Prior forecasts here, science forecasts here, and the real-time forecasts here. So you can see that the prior is much less correlated to the observation than both the data assimilation forecasts. But we can also see that the real-time forecasts aren't capturing the same standard deviation that we see in the observations. So this has led to what appears to be the real-time forecasts outperforming the science forecasts. It's not necessarily that they're doing better, it's just that because of the error metric that we used, they're producing a flatter forecast. So any small timing errors are being overly penalized by our error metric, which is making the real-time forecasts look as though they're outperforming the science ones, when actually it's not quite the case. Unfortunately, we didn't really have enough time to delve further into that and do all the analysis again with a different metric. But that just sort of gives a reason as to why it looks as though the real time is outperforming the science data. So looking to the future for SolarWind DA, the ESA Vigil mission is hopefully going to be launched. I haven't updated this. I think this has been pushed back to maybe 2029. I'm not sure, or 2027-ish, to the L5 point, which is 60 degrees behind Earth in longitude. So a little quote from ESA saying that the mission will give us advanced warning of oncoming solar storms, and therefore more time to protect spacecraft in orbit, infrastructure on the ground, and explorers now and in the future, unshielded by Earth's magnetic field and vulnerable to our star's violent outbursts. So this could be useful for future operational SolarWind DA. So to simulate this, I use combinations of spacecraft separated by approximately 60 degrees in longitude. And this was to simulate an L5 and L1 pairing. So for example, between the Vigil spacecraft and the Discover spacecraft. So I was using historic data to see how well this potential pairing could work for SolarWind DA. And this was using 4 time periods, as this little schematic shows. So we've got one in a few months in 2008, then in 2009 to 2010 and 2013 to 2014, using various combinations of stereo A and stereo B and near Earth. So this was for spacecraft between 50 and 70 degrees in longitude. So I had to choose a bit of a range because otherwise we just wouldn't have had enough time because the stereo spacecraft are moving in longitude. So this is a similar plot to before. This is showing all 4 time periods, but it's just a little bit easier if I show you the average of those 4 plots. So again, we're comparing with the prior. We've got just assimilating L1, so that's just assimilating the near-Earth data, and assimilating both the L5 and L1. So you can see that assimilating the 2 sources of observations leads to an improved forecast. So the L5 mission would add to our forecasting capabilities if we were just using L1 alone. But we can also see that when compared to L1 co-rotation, we're doing better for both experiments. But also compared to L5 co-rotation, so that's saying that the observations seen at L5, which is about 60 degrees, which corresponds to a forecast lead time of approximately 5 days. So saying that in 5 days' time, those observations will then be seen at Earth. And for a forecast lead time of sort of under 4.5 days, we are actually doing better than L5 co-rotation. And those forecast lead times are very important for space weather forecasting because of the transit time of CMEs. But the DA also offers an improvement over just co-rotation because we're reconstructing the entire domain, whereas for co-rotation, we just get point estimates. So where we have the whole domain reconstructed, that means that we can propagate CMEs through it, whereas you can't do that with just co-rotation. So even though this error is quite low and lower than a lot of the longer lead times, actually the DA is better because it means that we can do something with those predicted solar wind speeds. And again, this is just the Taylor diagram for that, and showing the 3-day forecast using L1 and L5 is the best one out of all of those. Yeah, there we go. So moving on from that, we've sort of got Bravda running operationally on a routine basis. So for this, we use files from the Met Office as part of the Swimmer project, if any of you know about that. And this is very new, so its initial plots are online, but it hasn't been verified yet. We're just sort of running it and hoping that, well, I should be doing the work to verify it in the future, but it's just very initial sort of tentative steps into getting this operational at the moment. So we get CME information from the Met Office, so that if there is one that's observed, this can run through the improved solar wind to give speed and arrival time updates. And this is kind of a world's first using solar wind DA, which is kind of cool. And I guess something I can say that's come out of my PhD. And this is just an example of some of the plots we're creating. So again, a polar plot. So this is from the 13th of November. And you can see that the prior has this fast stream here, which is then sort of being split up and said to be a bit slower, but also the DA is introducing this much faster stream, which you can see a bit clearer in the time series. So we've got the black line, which is without the DA, and the red line with the DA. So the line in the middle is the time that the forecast is made. So this is the past, and this is the forecast or the future. And you can see that the DA is bringing down the model run down closer to the observations. So it is improving our knowledge of the solar wind. But this example is a little bit boring because we don't have any CMEs. So if we get CMEs, this plot would show them. And I've got a little example of that from the 16th of September, which has 2 CMEs from the Met Office file. I have to say that they are unverified because I just don't have the time right now to be doing that. But this will hopefully form part of my postdoc, which I'm starting next year. But you can see here the difference between the two. So this top one is just the ambient solar wind, whereas this one has the CMEs in it as well. So the dashed line is the CME predicted arrival time without the DA, and the solid line is with the DA. So you can see for this one, the DA, the observations are saying that this solar wind stream is faster than what we thought initially, and also it's slightly shifted in longitude, so that it's saying that this CME arrival time will be sort of more than 12 hours earlier than what we initially thought. Oops. This one is a little bit similar, but the difference isn't quite as large. But yeah, so moving on for the future, we're hoping to verify the solar wind DA forecasts, including a large-scale study of CME speed and arrival time predictions, and hopefully see how using the DA boundary conditions would change when used in full MHD models, so the big models compared to the reduced physics ones, which these forecasts have been made using. So maybe using NLIL or maybe Euphoria, depending on how things go. And also I need to write a thesis. So yeah, that comes to the end. Just to conclude, the knowledge of the solar wind is important for timely and accurate space weather forecasting. The router scheme reconstructs a full solar rotation using the available observations, leading to improved solar wind forecasts. A future L5 and L1 spacecraft pairing could be useful for operational solar wind DA. And Bravda is running operationally using HUX with future plans to verify the forecasts. So there's a few references, and a lot of that work, not the operational stuff, which is very recent, was written up and published back in, I can't even remember when, earlier this year. And you can find the paper on that link or that QR code. So that's the end. Thank you for listening. I'm happy to answer any questions.
Awesome. Thank you so much, Harriet. There's a virtual round of applause this year, hearing from everyone while they're muted. Please be sure to make sure to check out Harriet's paper. We now have plenty of time for questions. If anyone would like to raise their hands or ask away, please, raise your hand, or please feel free to unmute yourself. All right, seeing none, I'll quickly ask the first one. When you're showing the difference between the real-time stereo B and the science level data, I was noticing there are some data gaps in the real-time, and I was wondering if you knew potentially how the science level was filling in those gaps. It looked to be a little bit more in depth than anything like linear interpolation. Yeah, so kind of right in the middle of the plot, there seems to be a data gap.
Yeah, that one. Honestly, I don't know. They have I guess they must have some sort of algorithm that can, I mean, there'll be different sensors. So I imagine it, yeah, I'm not sure. I don't really want to guess because I feel like that would be worse than just saying I don't know. But yeah, they'll have NASA will have their algorithms to fill in these gaps.
Okay, perfect. Yeah, I'll make sure to look it up because we, at least I do global manganese for MHD modeling, and we have to deal with data gaps for our boundary conditions. So if there's a better way to do it, it'll be interesting to check that out. David, I see you have a question.
Yeah. So one of the, well, I'll just say one. Validation is one of the kind of key things that we've discussed in the past about as an important factor for operational data assimilation. But one really common thing that tends to happen is the concept of, we'll call it geolocation error or timing error, which seems to be kind of the dominant source of error in your system. So I was just wondering whether or not you have any advice or thoughts on how to quantify collocation or timing errors in your system or in general.
Yeah, so we did think about this. I think for timing errors and things like that, we would need to look more at an event-based sort of verification, rather than using just like a blanket MAE kind of verification. I think my supervisor's got papers on event-based stuff, so that would be like picking out particular streams and seeing like how well they've been reconstructed. Other than that,
so like it's really common where we'll reproduce the structure. We do a really good job capturing the right scales and everything, but then we put it in the wrong place. And when you say have relatively discrete structures, so large anomalies from the background, and you put them in the wrong place, you end up with worse results in a mean square error sense than if you just didn't bother trying to capture them at all. So that's why I was just curious, that's all.
Yeah. I mean, that was the main difference we were sort of finding between the real time and the science, was just that the science forecasts were capturing those streams a bit better, but because they were slightly in the wrong place, they just looked like they were doing worse. But yeah, I think the event-based would, so taking each stream sort of individually and assessing the differences. I think you can use things like skill scores and stuff like that to investigate that a bit more. But yeah, assessing how the magnitude and the time sort of affects the forecasts. That'd be interesting to look at.
Thanks. Sorry, I'll let the next person ask.
Thank you.
Thanks. Go ahead, Jose.
Hi, Harriet. Can you hear me?
Yep.
Great. Well, first, thanks for the great presentation. I had a few questions. The first is sort of more technical, and then I have a follow-up question. But I think you might have mentioned it, but so you're correcting the sort of inner boundary of the corona, and that correction is steady, as it were, right? Like it doesn't change with time, but you get one correction per 27 days. Is that accurate?
So we have like a constant. So Bravta takes in the 27 days worth of observations, and that they're made hourly. So it's not just like 1 point every 27 days. It's actually so if I go back to so many slides. Yeah, this one. So we don't just have like one point, we've actually got loads of points the entire
Okay.
way around. So, and we
And
get it from multiple sources as well.
and I guess, so do you produce, so let's say you take in a whole host of observations. Are you correcting sort of one circle around the corona, and that sort of boundary condition is, or I guess what I'm asking is that boundary condition changing with time, or is that boundary condition steady, and then you're just sort of rotating the solar wind? I don't know. I'm not sure if the question is clear.
I guess it would be steady with time, I think. Until, yeah, because then you'd run it again and then you get new observations. So it might be a little bit different next time. But yeah, does that, I'm not sure.
No, that
Really
does
understand
answer
the
my
question.
question. I think, yeah, that answers my question, because, and the reason I'm asking this is because I'm wondering if you potentially had a time varying boundary condition, then potentially you could even get sort of a CME propagation in your simulation almost for free. So you're not actually injecting a CME into it, but potentially you're actually getting, you know, that the sort of structure of that CME by data simulation. Or I'm not sure if that would be the case, but that's sort of a question I have. Like, have you thought about that, or do you think that would work out that way?
I'm not sure about, because BRAFTA itself has no sort of knowledge of CMEs. So if it detects, if a CME is detected at one of the observation sources, for example, if it hits like stereo A, then BRAFTA would reconstruct that as a fast stream rather than as a CME. And I've looked, so my previous paper that was published last year looked into this a little bit more. And the more observation sources we have, the less that impacts how the quality of the forecasts. So if we only had one observation source, that like fast stream might persist for quite a while. But if we get a CME at one observation source, but then not at, for example, one up here, that would lessen the impact of it.
Okay.
Because it's seen in one place but not somewhere else. So more observation sources helps to reduce that effect. I also looked at removing CMEs from the input time series, and removing them did improve the forecasts, but doing that in real time is very challenging. And
I imagine,
yeah, because there's a lot of like identification issues with removing CMEs from a time series in real time. But
so you're actually taking like for example, ACE data and trying to erase the effects of the CME just to get the background. Is that what you're?
We're not doing that for this work, but my previous paper I did look at, well, there were hindcasts. So it's kind of, looking at it with hindsight, but doing that in a real-time sense is difficult.
Right. Okay, well, thanks a lot.
Thank you.
Can I ask you a quick question, building on Jose's question? Do you actually say what the method is? It is is that like a variational type of method that you're using, or?
Yeah, so it's essentially 4D VAR, but instead of time, it's radius.
So radius, okay. So that's why you're taking the observation taken over time and then optimizing the boundary condition.
Yeah.
Okay. Yeah. Thank you. Yeah.
Thanks. Do we have any other questions for Harriet at the moment? All right.
A bit of, so you say that, Harriet, thank you very much for presenting. And then you said that, you're going to write a thesis. And then, so what is actually still, it's it's a really probably time consuming to analyze and then run this operational system, as with any case. But, what is actually still sort of, your burning sort of next step or desire to take this work,
Yeah, yeah, so my next few months is writing a thesis, but then I've got a postdoc lined up, basically continuing the same set of work. So I guess we'll probably be starting off by looking at, because we're starting doing these kind of operational runs, and hopefully in the next sort of 6 months before I start the postdoc, we'll hopefully build up a bit of an archive of these, or 6 months worth of runs done every 6 hours. And hopefully I can look at these and verify and see how well they're working, and look at the CMEs as well. So that'll probably be a big chunk to start with.
Are you able to put the hypothetical observatory different places to see, basically OC type of research?
It's not something we've really thought of. I guess there's probably a lot of experiments that we could do with sort of like generated data and like fake data kind of thing. But everything we've done, or I've done, has been using real observations rather than simulated ones. But that is definitely something that we could look at.
Yeah, lots of possibilities. Yeah, thank you very much.
Thank you.
Back to Adam again.
All right. Well, I don't see any further questions. So let's all thank Harriet again and wish her the best of luck in these upcoming months writing her thesis. Please check back later this month for the link to this video that we'll upload to YouTube. And also, hopefully, we will see most of you in 2 weeks at the upcoming GeoDAWG workshop follow-up. So thank you all again, and we will see you either in 2 weeks or at the next GeoDAWG seminar series. So thanks, everyone.
Thank you.
Thank you, everyone. Thank you, Harriet. Bye.
Bye.
Thank you.